Hello there, AP Stats classes. Mr. Eicher here. Wanted to do a quick review so you have all the formulas in one place. Many of these formulas about sampling distributions are provided on the formula sheet on the AP exam. You get the formula sheet on the multiple choice section and the free response section. However, this column, none of this information is provided on the formula sheet. So you definitely need to know how to tell if the shape of a sampling distribution is roughly normal. So we have, in this chapter, we had 4 different sampling distributions. We started with the sampling distribution of p hat. So if you take a sample, find the proportion, like the proportion who like the color green, and you take repeated random samples from some population, calculating a bunch of sample proportions, and then find the average of all those p hats, mu p hat, the average of all the p hats from all possible samples, then that would equal the population proportion. So if, I don't know, 20% of all Americans like the color green and you took a random sample, you're not going to get 20% every time. But on average, if you take all of those sample proportions that you possibly could get, then on average that will equal the 20% in the population. The standard deviation would be the standard deviation of all those p hats, and that would be the square root of p times 1 minus p over n, the sample size. So the standard deviation tells us how much we expect p hat to vary, typically from sample to sample, vary from the mean of the sampling distribution. And then the shape, we have an approximately normal shape if 2 things are true. First, the number of successes, n times p, is greater than or equal to 10. And n times 1 minus p is greater than or equal to 10. So that's our first sampling distribution that we looked at. Next, we looked at p hat 1 minus p hat 2. So taking independent random samples from 2 different populations, we would have a mean of p hat 1 minus p hat 2. The mean of all those differences in p hats would equal the first proportion, the first population, minus the population proportion in the second population. And the standard deviation, I'm going to zoom in so I make sure I fit this. The standard deviation of p hat 1 minus p hat 2 equals massive square root, the first population proportion, 1 minus that first, over the sample size of the first, and then the second times 1 minus the second over the sample size of the second. And to determine if the shape is approximately normal, so approximately normal, if 4 things are true, you basically check the same condition we did before, but for each individual sample. So the first sample size times n1 times p1 is greater than or equal to 10. n1 times 1 minus p1 greater than or equal to 10. n2 times p2 greater than or equal to 10. And n2 1 minus p2 is greater than or equal to 10. So those are our first 2 sampling distributions. The next one we learned about was the sampling distribution of xbar. So you have a population, take a sample from that population. You find the sample mean, that's xbar. Repeat that process, take a bunch of different random samples until you have all possible random samples. Plot all of those xbars, and that would be the sampling distribution of xbar. So if you found the mean of all those xbars, the mean of those xbars would equal the population mean, mu. This looks kind of weird, mu sub x equals mu. You have a lot of mu's here. But on the left side, that's the mean of a bunch of xbars. On the right side, that's the population mean. And the standard deviation of xbar is the population standard deviation, that's sigma, capital sigma, or not capital, lowercase sigma in Greek, it's lowercase. And then divided by the square root of n, the sample size. And the shape is a little bit tricky to write all the options. If the population is normal, then automatically the sampling distribution is approximately normal, I should say, approximately normal. If the sample size is large enough, then the sampling distribution is approximately normal. And that theorem is the central limit theorem. It's CLT, central limit theorem. And that's probably one of two theorems we talk about. We talk about the Pythagorean theorem of statistics, and we also talk about the central limit theorem in this class. Not too many theorems in this class. And then lastly, we have x bar 1 minus x bar 2, the sampling distribution of the difference in means. So the mean of x bar 1 minus x bar 2 would equal the population mean for the first minus the population mean for the second. And the standard deviation of x bar 1 minus x bar 2 is big square root the population standard deviation from the first squared, that's the variance, over the first sample size, and then the population standard deviation of the second squared, and that's over the sample size of the second. For the shape, we would need to know both populations. If both populations are normal, then automatically the sampling distribution is approximately normal. If not, if the shape is like left skewed or right skewed or bimodal or some weird population shape, you would need to check that both n1 is greater than or equal to 30 and n2 is greater than or equal to 30. And if that's the case, then the sampling distribution will be approximately normal. So we have conditions under the shape column. It might be good to include that all of these centers in this first one rely on the fact that we're taking random samples. So we call this like the random condition to make sure that we get unbiased estimators. And then the spread relies on either the observations being independent or the 10% rule, that the population has to be 10 times bigger than the sample. Or conversely, to say it the other way, the sample has to be less than 10% of the population. You can see the 10% rule written like this. Our textbook writes it like this, where lowercase n is the sample, has to be less than or equal to 1/10, that's 10%, of the population size. And then capital N is the population size. And we often don't know, capital N, what the population size is. So we usually typically just say, well, we're sampling without replacement, so we'll assume that the sample is less than 10% of the population. And I see right down here that the continuation of these notes we'll save for another day. So thanks for watching this video. Give me a thumbs up if you made it this far. Thanks for making it this far. And I hope it was helpful to have all the formulas in one place. See you next time.